Hello, I'm Bradley Alisi. I'm head of the DevoWorm project. There's our website at the top of the screen. And in the bubbles, which are supposed to be cells, you see the names of collaborators who have worked with us for the last 2 years or so. We have 3 interest groups, which are in the cells in the lower left-hand corner. I met Steve Larson in April of 2014, and right away we started working on a couple of things. One was a technical paper, and the other was a journal club laying out the major problems of this task, which was to deal with the developmental component of OpenWorm and to understand how the worm develops into the adult form that people were trying to simulate in the OpenWorm project. We deal with empirical science, data science, and artificial life. The data science are secondary analyses. The empirical and artificial life components are primary works from our collaborators. And we've actually moved away from that original technical paper and gone in new directions, which have led to a number of other publications. We have a couple of newer publications this year that have really kind of shown how the project has grown, and you can see that from the DOIs on the screen. We've also delivered a couple of talks, internal and external, to OpenWorm since that time. So we've actually made some big strides. The development of C. elegans, why are we interested in it? Because it's a deterministic system. It produces a deterministic lineage tree, which is invariant between embryos. So we go from embryo all the way to adulthood. And in between, we look at the cells and how they differentiate it from single developmental cells into whole tissues. And so the adult organism is eutelic, has a fixed number of cells in each worm. So we can actually trace, theoretically, every cell in the worm from its inception in the embryo to the adult form. Now, this is a time series problem, so we have a lot of dynamics to deal with. We have, for example, we can look at this embryo over a series of minutes. This is over a series of 200 minutes. So over time, you can see that cells are born from the developmental cells and differentiate into different tissues. And we can look at the patterns over time for each different type of tissue, whether they be neuron, interneuron, or hypodermal cell. Now, our inspiration is the lineage tree, first mapped out by John Sulston. And as you can see, you go from the zygote and from the single cell all the way down to a whole host of tissues which make up the adult worm. It's a process of branching, but it's also a process of timing. And that is one of the reasons why we're looking at differentiation trees, which is something that one of our collaborators, Dick Gordon, has come up with. On the right, we have an axolotl embryo. And in the middle, we have a differentiation tree for the axolotl, which is based on the differentiation of tissues over time and their relative size relative to one another. And that gives us information about differentiation. So in this example, we've made a differentiation tree from a lineage tree in C. elegans, and we can look at larger cells as being analogous to an expansion wave and smaller cells being analogous to a contraction wave. And those terms are relevant to differentiation tree theory or differentiation wave theory. This is something that you can read about more from Dick Gordon's work. This is an abstraction of embryogenesis as a dynamic process, and on the right, we've built a differentiation tree from this process. So it's very easy to see how the process of differentiation, especially asymmetric differentiation, maps to a tree structure. Now, we've been interested in comparative development as well. So we've been interested in C. elegans, of course, but also comparing the results in C. elegans to Ciona intestinalis, which is a sea squirt, and axolotl, which is an amphibian. And you can see we're covering the tree of life here. We've got 3 model organisms already, and we've got the differentiation trees for those. But we're also interested in looking at Drosophila melanogaster, which is an insect. We have data for the imaginal disc, and mouse, Mus musculus, where we have data not quite towards what we would call a differentiation tree, but we're interested in all modes of development all across the tree of life. So model organisms beyond worms, basically. Now we switch gears to something that Tom Porteges will give a talk on in one of the tutorials, which is morphozoic. This is a nested cellular automata, which we can use to look at pattern formation in a developmental context. So in his case, We have what we call nested neighborhoods, which are neighborhoods of different sizes nested in one another. And what you can do with Morphozoic, you can download it from GitHub, and you can run something similar to Conway's Game of Life, where you look at the interactions between cells, and they produce patterns representing phenotypic forms. And they're just basically simple rules that get employed in the interactions between the cells and their states, and it produces these shapes. For example, gastrulation. We have gastrulation. We can get that from a sphere. And this relates to Richard Gordon's spherical cow problem, and that is, how do you get an asymmetric phenotype like a cow from basically what is a sphere, which is an embryo? And you can see the process of gastrulation. We're starting to get some asymmetry in the form. So we can use Morphozoic to verify some of those things. We also have an empirical science component. One thing is experimental evolution of fecundity. So in this case, we're comparing wild-type phenotypes with mutant genotypes, and we can see their population size over evolutionary time, and we can look at how certain traits evolve in different genotypic backgrounds. And in this case, we can actually also look at reproductive plasticity with regard to stress. In this case, it's a starvation stress in the larval stage. So when larval worms get starved, they have a different profile than when they don't get starved. And this is also true for different genetic backgrounds. This is an example of the wild type, but we can do this for genetic mutants as well. Future directions for the project include building cellular level physics models, looking at self-organization as a mode of organizational information, looking at things like cybernetic models, and doing the data science of high-resolution imaging and other types of data sciences applied to this problem. We have a project website, we have a Gitter channel, we have a YouTube channel, and we have weekly meetings, Mondays at 4 p.m. Central Time. There's the link to the Google Hangout. We also have a link off of our website. And if you're interested in volunteering for this or any other OpenWorm project, there's a link at the bottom of the page that will give you more information about that. Thank you for your time.